Lithium-ion cells operate reliably within a specific thermal window, between 20 and 40 degrees Celsius. Temperatures below this range spike internal resistance, while temperatures above it initiate the breakdown of internal chemistry. Strict thermal uniformity is equally critical. The temperature difference between the hottest and coldest regions of the module, or delta T max, must stay below 5 degrees Celsius to prevent cells from aging at different rates and creating pack-level imbalances. Pushing a cell beyond these boundaries triggers immediate degradation. High heat accelerates side reactions that permanently thicken the solid electrolyte interface layer on the anode, stripping the battery of its total charge capacity. Left unchecked, this heat accumulation initiates a self-accelerating exothermic reaction. The internal temperature continues to climb until the polymer separator melts, causing the cell to violently vent flammable gas in a thermal runaway. High-rate fast-charging protocols force massive amounts of current into the cell in minutes. This generates a thermal load that violates these operational margins, creating a bottleneck that standard single-mode cooling systems cannot resolve. Using the Bernardi model, we isolate thermal stressors during 5C discharge. First is irreversible joule heating. As current meets internal resistance, electrical energy converts into a continuous thermal load. Second is reversible entropic heat, produced by chemical reactions, which fluctuates with the state of charge. This schematic outlines our computational domain. We employ a half module with a symmetry plane to map these specific heat sources with high numerical efficiency. Accurately quantifying both the steady ohmic heat and the shifting entropic heat is the required first step before engineering a conjugate heat transfer system capable of dissipating them. Our baseline configuration, Design 1, is an industry-standard monolithic aluminum cold plate featuring 5 internal microchannels. It operates via forced convection. A water glycol coolant circulates through the channels, absorbing heat through the aluminum walls to be rejected at an external heat exchanger. Under high transient loads, monolithic aluminum fails to distribute heat quickly enough. Severe, localized hotspots form at the center of the cells, driving the temperature gradient beyond the safe 5-degree limit. The standard engineering response is to increase the coolant velocity. Pushing more liquid through the channels drives heat rejection upward. However, forcing liquid through microscopic channels creates immense hydraulic resistance. The required pumping power climbs exponentially, exceeding the thermal benefits. This creates a significant parasitic power loss. The battery must expend its own stored energy to power the pumps, directly reducing the vehicle's total effective driving range. Brute force fluid velocity is an inefficient way to manage transient heat spikes. The system requires a passive thermal buffer to handle the initial thermal shock without draining battery power. We integrate a 0.5 mm layer of phase change material directly between the battery cell and the cold plate to act as that buffer. As the battery heats toward the 40-degree threshold, the material transitions from solid to liquid. On a temperature graph, the rising curve flattens into a plateau. This isothermal buffer absorbs large quantities of latent heat, artificially clamping the battery's surface temperature during aggressive discharge. Explicitly tracking this moving solid-liquid boundary, known as a Stefan problem, is too computationally intensive for a full 3D battery module simulation. We solve this using the apparent heat capacity method. By modifying the specific heat equation, we mathematically distribute the latent heat over a narrow temperature range, ensuring a stable numerical solution. The simulation reveals a critical physical flaw. Once the material fully transitions to a liquid, its thermal conductivity drops to just 0.2 watts per meter Kelvin. In this state, the liquid material becomes a thermal insulator, trapping residual heat against the battery casing and preventing the coolant from reaching it. While the phase change layer successfully absorbs the initial thermal shock, it will eventually cause the battery to overheat unless it is paired with a highly conductive frame to extract the heat and re-solidify the buffer. This leads to Design 3. We replace the monolithic aluminum with a graphite fiber reinforced aluminum cold plate, which encapsulates the phase change material. This composite is defined by its anisotropic thermal conductivity. Unlike aluminum, which transfers heat uniformly in all directions, the composite's thermal properties change depending on the axis of the graphite fibers. Along the horizontal X and Y planes, the graphite fibers provide a conductivity of 240 watts per meter Kelvin, pulling heat laterally across the plate. Simultaneously, the composite meters heat downward through the z-axis at a steady 30 watts per meter Kelvin into the microchannels. This lateral spreading eradicates localized hotspots instantly. By distributing the heat, the composite ensures the entire volume of the phase change material melts at the same time, maximizing the buffer's effectiveness. The liquid microchannels then continuously drain the heat from the composite, allowing the phase change layer to re-solidify and reset for the next dynamic load. By assigning specific thermal duties to separate layers, lateral spreading to the graphite, transient buffering to the PCM, steady rejection to the fluid, the system manages dynamic loads without the parasitic power spike required by conventional pumping. We compared the thermal performance of the baseline aluminum plate and the hybrid composite architecture during a continuous 5C high-rate discharge. The CFD results show Design 1 reaching localized thermal saturation, while Design 3 maintains a dispersed thermal equilibrium. The hybrid achieved a 25% reduction in maximum temperature compared to baseline and a 30% improvement in uniformity, keeping the gradient below the 5-degree threshold. These results demonstrate that managing high power density requires shifting focus from fluid velocity to the precise engineering of thermal impedance through composite materials. To test the limits of the design, we ran a final edge case simulation, an aggressive 8C discharge rate in a hostile 45 degrees Celsius ambient environment. In these conditions, internal heat generation is compounded by inescapable environmental heat. This combination typically triggers the chemical breakdown that leads to thermal runaway. The GFRA and phase change system successfully halted the cascade, maintaining a maximum temperature difference below 17 degrees. Even when active cooling is overwhelmed by ambient conditions, the multi-layered architecture provides a physical barrier that protects the internal chemistry of the cell. This multi-layered conjugate heat transfer architecture provides the safety margin necessary for lithium-ion modules to survive the extreme thermal stressors of high-rate fast charging.